So first of all, I would like to thank you for inviting me to give these lectures in memory of Ernest Nagel. I have many colleagues and friends here in Pittsburgh with whom I've interacted quite a lot over the years, but it so happens that this interaction has taken place in various other places and never before here in Pittsburgh itself. This makes me especially glad to be here. I will take my starting point in a theorem found by Lindenbaum and Tarski at about the same time as Tarski wrote his most widely known and widely influential papers, the Wahrheitsbegriff paper and the paper on the logical consequence from 1935 and 1936 respectively, although the Wahrheitsbegriff paper in Polish was already in 1933, but very few could read it in that form. Now this theorem is on the blackboard, and it's a theorem that is would have been very little known, presumably, had Tarski not returned to it, as I will explain in a moment, some 30 years later, which caused a considerable interest in it from the 60s and onwards. Now, what the theorem so Tarski works at this time within the context of the simple theory of types, and it's clear that it is before Church's formulation of the simple theory of types from 1940. Because the type structure that Tarski apparently presupposes is the older type structure that you find in Carnap's Abriss der Logistik, for instance. Maybe that was the first place, from 1929. So it's the type structure which is generated by saying that we have one base type, 0, which is the type of individuals, and then given types τ1 up to τn, we can form this new type, which is the type of n-place relations with arguments of type τ1 up to τn, respectively. And that is supposed to include the case when n is equal to 0. So this is the type of propositions, simply, Church's omicron. So this corresponds to Church's iota, and this is corresponds to Church's omicron. But you see, Church allowed any kind of higher types formed by means of these two ground types, whereas here you are only forming higher types of this special form. So it's a more restricted type structure. Now what the theorem says, you see here that every sentence or formula, if you want, of this form, and here I've allowed myself to deviate from the paper itself, because strangely enough, Tarski was so attached to simple type theory at the time that he even wrote it in the notation of in the dot notation of Principia Mathematica, a notation that was invented by Peano, and which makes it almost unreadable for most of us nowadays. But I retained the signs for the logical operators. So this is a sequence of universal quantifiers. And here is presupposed that x prime and x double prime are variables of the same, possibly higher type. And similarly with y prime and y double prime, z and prime and z double prime, etc. There is, of course, only a finite list of such pairs of variables here. Then comes the quantification of a relation R, which is a relation between individuals. And Then comes a curious abbreviation here for a complex formula, which I will explain in a moment. And then there is a formula sigma that is a term of propositional type, which may depend on these variables x prime, y prime, z prime, etc. And on this side, we have the same formula with the variables replaced by x double prime, y double prime, z double prime, etc. And this is the sign for logical equivalence, material equivalence. And so what remains is only to explain this curious expression. And it's defined. So this says, first of all, that the relation R here, which is a relation, as I said, between individuals, R is to be 1-to-1. And that we know, of course, so I need not say anything about it, I suppose. For all, we can put it in the form for all x that there exists a unique y, and for all y there exists a unique x, such that rxy, for instance. So R is 1-1. That's just a first order formula, since R is a relation between individuals. And then comes the information about this, and this is that x prime stands in the relation R to x double prime. Now this needs explanation, because if x prime and x double prime, which have to be of the same type, are of the type of individual types, then this of course means that they stand in the relation R to each other. But if they are of higher type, it should mean that it has to be defined by induction on the type structure. So for let's take simplest higher type, namely the type of classes of individuals, say. Then it says that x prime, x double prime is the class of individuals x prime carried over via the relation R. So that's sufficiently clear, I hope. And similarly, if they are, say, relations between individuals, then those relations should correspond to each other, in the sense that if the arguments correspond to each other in the relation R, then x prime holds of those arguments if and only if x double prime holds of the correlated arguments. And this can clearly be continued up through the finite type structure by induction on the build-up of the types. And this, to my knowledge, is the first occurrence of the idea of logical relations. That is, a relation R which has to be defined separately at each type, and the definition is by induction on the build-up of the type. So x prime and x double prime should correspond to each other in this way, and similarly then for y prime and y double prime, which are now of another type, but the same type, and so on, z prime or z double prime, and etc. So in words, what this curious formula says is that R is 1, 1, and that these variable pairs correspond to each other in the relation R blown up through the higher type structure. And hence, what the whole theorem says is that if we take any sentence of the simple theory of types, sigma, then it is invariant under all isomorphisms, since R is supposed to be 1, 1, under all isomorphisms of the individual domain, invariant in the sense that if the arguments correspond pairwise to each other in the relation R, then sigma holds of the primed arguments if and only if sigma holds of the double primed arguments. So we can summarize it by saying that any definable term, or since it's a propositional type, any definable proposition in simple type theory is invariant in this specific sense. Now, as I hinted at before, had it been just for this this technical result, this theorem would presumably have been little known. But 30 years later, in 1966, Tarski gave a lecture at Buffalo in which he proposed to use invariance as in order to make precise the distinction between logical and non-logical constants that he had used in his paper on logical consequence, also from 1936, and which the last 2 pages of which consists of expression of his expression of his dissatisfaction with that distinction. I mean the distinction between logical and extra logical, as he said, außerlogisch. Now I guess we more normally say non-logical. And it was crucial in his definition of the notion of logical consequence that he had a distinction between logical and non-logical constants. And the problem was that in his mind at that time, that distinction was fairly arbitrary, which is to say just stipulatory. Certain constants we call logical, other constants we call non-logical. And he was clearly dissatisfied by that. And this proposal from 1966 in a paper called, so in a lecture originally, but nowadays in a paper called What Are Logical Notions? And it became a paper because it was taped, and not long before Tarski died in '83, he asked John Cochran to edit this paper, which shows that Tarski attached a considerable importance to its content. And the proposal of Tarski's was to use invariance as the criterion for logicality. That is, to define an operator or a constant to be logical precisely if it is isomorphism invariant in the sense that I have already explained. And this clearly makes all the standard logical constants logical, because they are expressed, can all be expressed by means of such a sentence sigma as appears in the theorem. Now, it seems to me that this problem of making precise the definition between to draw a sharp division line between logical and non-logical constants has come in a completely new light as a result of the Curry-Howard correspondence, which appeared only 3 years after 1966, in 1969. Because, and I take it that the Curry-Howard correspondence is known to everybody here. What does the correspondence consist of? Well, it's summarized in a table with 2 columns. And in one column, you have logical notions like a proposition, truth of a proposition, the connectives and the quantifiers, and so on. In the other column in the table, you have set theoretical notions. So instead of proposition, you have set, or I guess originally Howard said type, but I think I will stick to set in these lectures. So you have set, and you have inhabitedness of a set corresponding to truth of a proposition. And then you have the set theoretic operations of Cartesian product, disjoint union, forming the set of functions from one set to another. This corresponds to the connectives. And then for the quantifiers, you have a Cartesian product of a family of sets and disjoint union of a family of sets. And this can be continued on and on. But the whole idea of the Curry-Howard correspondence, if you take it to its extreme, so to say, is that what we have in these 2 columns are just different verbal manifestations of the same one and the same conceptual structure. So it's a synonymy, really, that we have between the 2 sides. And since the 2 sides are labeled logical, respectively set theoretical, this means that it's a complete obliteration of the distinction between logical and set theoretical notions. And if now Tarski did not say set theoretical here, he said extra logical. But if you look at what he had in mind, I mean, it's clear that among what he had in mind with the extra logical things are the arithmetical things, and above all the set theoretic ingredients. So a complete obliteration of this distinction between logical and set theoretical notions. So maybe I could summarize the situation. In a table like this, a fourfold table. So we have the logical and the extra logical or non-logical notions. So it's precisely this dividing line which is obliterated by the Curry-Howard correspondence. But there remains at least one distinction which is completely clear and completely sharp. So one need not be concerning that distinction, one need not have Tarski's worries. And that is this distinction between interpreted and uninterpreted constants. And if we now place the standard constants from first order logic in this fourfold table, it's clear that the connectives, the truth and falsity, and the connectives and the quantifiers should count as logical. There's no discussion about that. And they also have meaning, of course, their standard meaning. Whether it's classical or intuitionistic, I mean, the meaning explanations are different if you have the classical or the intuitionistic interpretation, but at least everybody agrees that they have meaning. And there is the question about, I can wait with equality for the moment. Then non-logical constants, what comes first to mind, as I said before, is in arithmetic. You will have a constant for the domain, individual domain of the natural numbers, and you will have zero successor. You will have plus and times and so on. And if we have set theoretical notions, they will, of course, also fall here. Now, as for the uninterpreted constants, what we normally think of then are, of course, first of all, the individual domain in first order logic must belong to the set theoretical, that is the non-logical. And then we have the individual constants and the constants for individual functions. Let's call them f, g, h, etc. Mappings of possibly several arguments from D to itself. They should clearly count as non-logical. And then we have the relation symbols, P, Q, R, etc., which are also uninterpreted and standardly considered to be non-logical just as much as these are non-logical. So this is just the prevalent view that they are non-logical and uninterpreted. Now this part, the fourth square here, is usually left empty. But of course, we can very well have a symbol little c, say, for a connective, that is with two propositional arguments and gives a proposition as value, which is left uninterpreted. No problem about that. And we can have a quantifier q, so that we can write qx, say, p of x or something like that. A quantifier q, which has the same type as the well-known quantifiers, but which is left uninterpreted. So in this case, we would have uninterpreted logical constants also. Now, I haven't said anything about identity or equality yet, and that depends on how you interpret the equality symbol. One in the most basic way is to interpret it, to think of it as interpreted by saying that it's the least reflexive relation, or it's defined by the introduction rule that T is equal to T, if you want. Equality introduction. And if we understand it in that way, then of course the identity symbol or the equality symbol is interpreted, and it must be put in this square for the simple reason that logicism wouldn't have a chance even without identity, because identity is used on the first pages of development of the logicist program. So I think we definitely should put it here. Now, there is another treatment of equality which is much more mathematical, namely to treat the equality relation simply as any equivalence relation on the individual domain D. So it's which means making D into a setoid in the terminology that has become prevalent, set equipped with an equivalence relation. And if we, on that choice, it is left arbitrary, so we have to put the equality arbitrary, which is to say uninterpreted, so we have to put it here. And then we also have to include axioms saying that the function symbol, the functions respect this equality and the relations respect the equality. So this is a much more mathematical treatment of equality, which makes it uninterpreted rather than interpreted. Now, if the Curry-Howard identification of logical and set theoretical notions obliterates this distinction, so now these two lines are of the same kind, then there remains at least this distinction between the interpreted and the uninterpreted symbols. And this distinction is the only one which is needed in the definition of, in Tarski's definition of logical consequence. Of course, it's not any longer so natural to call it logical consequence, since that was tied to this term. But his definition of logical consequence is, after all, that the consequence should hold however we interpret the uninterpreted symbols. And so maybe actually from a terminological point of view, if you accept this consequence of the Curry-Howard identification, to go back from the term logical consequence to the original term, which was formed in the 14th century, formal consequence, and Tarski was fully aware of this. In certain places in his paper he uses the pair of words formal as opposed to material, rather than logical consequence. So, and the or at least one of the definitions of formal consequence, consequentia formalis, from the 14th century, the formulation is, I think, from Buridan, is that a formal consequence is that which holds in all terms, which is to say, under variation of all terms. It's precisely the idea that all the uninterpreted constants should be allowed to take any value, to be to be varied. Consequentia formalis est illa qui tenet in omnibus terminis was this classical formulation. So that means that the notion of logical consequence remains intact, except perhaps we would now prefer to call it formal consequence. And we get completely rid of this problem of drawing the dividing line between the logical and the non-logical constants, and replace it instead by this dividing line, which is sharp enough. Now the next step here is to go over to the proper content of these 3 lectures, which is to give an analog of the Lindenbaum-Tarski theorem, which deals with the simple theory of types, as I've said, to give an analog of it for constructive type, intuitionistic or constructive type theory. And now that's a big step in the sense that the simple theory of types is classical, well, as Tarski and Lindenbaum dealt with it, it's classical as opposed to intuitionistic. It's, I haven't said that before, but Lindenbaum and Tarski presupposed classical extensional simple type theory, so it's extensional, versus intuitionistic type theory, which is intensional. And one could add here that classical simple type theory is, of course, also impredicative, versus intuitionistic type theory, which is predicative. So there are at least 3 very important distinctions between the classical simple type theory and intuitionistic or constructive type theory, which means that there are considerable changes that has to be made to the Lindenbaum-Tarski theorem. So the first thing in dealing with intuitionistic or constructive type theory you see I still can't quite make up my mind which term to use, and the reason is, I think, the following, that I originally used intuitionistic type theory because I thought that the standard division line in between classical and intuitionistic. But then when you abbreviate intuitionistic type theory, it becomes ITT, and then someone drew my attention to the fact that that's International Telephone and Telegraph Company, the most used acronym for that, so it wasn't so good. And then CTT had no such problems, and so construct.
CTT is the mail system.
Ah, so it's just as bad.
It's not as bad because nobody uses mail anymore.
Yeah, very good. Anyway, so there are more arguments for one or the other, and not clear yet which wins here. But any presentation of intuitionistic type theory has to begin by simply displaying in the form of a table the 4 basic forms of judgment. And they are that something is a set in a context where finitely many variables are typed, and that 2 sets are definitionally equal. I have mostly used definitionally equal. Here you can also say judgmentally equal, also in a context of that sort, and then that A is an element of the set capital A in such a context, and that A and B are definitionally equal elements of capital A in the same kind of context. So these are the 4 basic forms of judgment of constructive type theory for the original system. Now, when the higher type structure was added to type theory in 1986, the same pattern here repeated itself, but then capital A and capital B here are no longer sets, but possibly higher types. So we get instead that, say, and now I change then the schematic letter to a Greek letter for types. Alpha is a type in the context when x1 is of type alpha 1, etc., xn of type alpha n, and alpha is definitionally equal to another type beta in such a context, and A is an object of type alpha in such a context, and A and B are equal objects, definitionally equal objects of type alpha in such a context. And the types here, they are generated by the 3 rules of type formation, that a set is a type, and then remember that because of Curry-Howard, set is the type of sets is identified with the type of propositions. And then we have the rule that if A is a set, then we may form the type of elements of A. So element of A is a type, and in the logical reading we read instead capital A is a proposition, and the element of A we read as proof of A. So the type of proofs in the intuitionistic sense of proof objects is a type, and then we have the dependent function types, that if alpha is a type and beta is a type, possibly depending on a variable x ranging over alpha, then the dependent function type x alpha beta is a type, and we discharge that assumption. So this generates the higher type structure, which is a dependent generalization of Church's simple type structure. You see, this is just like Church's omicron, and if we have no dependency, this boils down to the function type, Church's function type, and the difference is here that whereas Church had one type iota of individuals, only one fixed, here any set gives rise to a type. I could write element of A just as well as iota of A, say. So any set gives rise to a type of individuals, iota of A. And that gives rise to the possibility of having beta here depending on x, and hence to have a dependent function type here. So, but one should remember that this is just a dependent generalization of the well-known simple type structure. And of course, this now contains the original 4 forms as special cases, namely if we take alpha. So all these 4 forms become instances of these 2 last forms here. If we choose alpha to be set, then we get this. And if we choose, and also when we choose alpha to be set here, we get that. And if we choose instead element of capital A here and there, then we get these 2 forms as special cases. So the type theory with a higher type structure is a more expressive system. Now I'm going to try to explain something new, and which is a bit difficult and surprising, because here I have, after all, displayed the forms of judgment in constructive type theory in a completely formal logical notation. So one might think that, well, then all ambiguity is eliminated. I mean, we are used to ambiguity in something written in natural language, and when we formalize it in predicate logic or something, we precisely impose on it a precise logical form. But here it is a formal language already. But nevertheless, there is a question about what the logical form of these judgments are really. And that has to do, it's not a purely syntactical matter, it has to do with how they get their meaning. So I will start by proposing that we, and it's sufficient now for my discussion that we consider the lower level here. If we call this lower level and this the higher level. To look at them simply as declarative sentences in natural language, and ask ourselves, what is it, what is the subject and what is the predicate? What is it that something is said about the subject? So we ask for the subject. And what is it that is said about that something? We ask for the predicate. Then if we put it that way, then we are imposing on this simply the subject predicate form, which traditionally is written S is P, or of course nowadays NP plus VP, but let me write it in the traditional form, where in English and our most common languages we need an indefinite article here. I mean, S is a P rather, but I will stick to the usual form here because in the classical languages there is no indefinite article. So it's the Latin est P, and this is the Greek analog, which I note because of the first letter here. This is the origin of the epsilon for the copula. So piano, choose epsilon because it's the first letter of the Greek ST. Now, how is this something of this form? Well, this says of capital A that it is a set depending on these variables. So the predicate P is all of this, and this is the subject. And similarly, in the third form here, it says that A is an element of capital A depending on these variables. So the predicate is element of A depending on these variables, and the subject is little a. And then we have the remaining, the second and fourth form here, which is clearly not of this form, or not immediately at least. It's rather of the form S1 equal S2 colon P, say. Of course, if we analyze it grammatically, we would say that A and B is the subject. A and B are equal sets depending on these variables. So A and B would become the subject. But as logicians, we of course immediately take the step and think that it's more natural to think of them as two subjects in this case as opposed to just one subject here. So that means that it instantiates this form, and similarly this instantiates this form, where now S1 corresponds to little a, S2 to little b, and the predicate is all of this. Now, on this analysis, we see that the four forms become 4 by being 2 times 2. So we the P we choose for P here either set in this context so this is for possible choices for P, or element of A in this context. These are what we properly should call categories. And so how is category connected with predicate that we have here? Well, in linguistic terminology, this is the subject-predicate form. But in logical or ontological terminology, this is what is called the category, and this is an object of that category in standard terminology. So subject is transformed into object and predicate into category. And why is predicate connected with category? Well, it's because the original verb was kategorein in Greek, which means which was translated predicare, which means predicate. And hence from this kategorein in the background, we have both predicate and we have category, which is kategoria in the Greek, and predicate is the categoreumenon, so they are both derived from the verb categorein, predicate. And hence, it's only in the modern languages that there seems to be a wide difference between category and predicate. So now we have an analysis of these four forms of judgment into two forms now, the S is P form and the definitional equality form, where the category here in turn, P, can be chosen to be either of this form or of that form. Now, how is the notion of category pinned down? To my mind, the correct explanation of the notion of category is that a category is defined by laying down two things. First of all, what an object of the category is, and secondly, what it means for two objects of the category to be the same. So P is defined by explaining what an S of category P is and what it means for two such S's to be equal. So there are two things here, and the second is what we call the criterion of identity using Frege's term, and the first, I'm following Dummett. It may go further back, but I have certainly learned it from Dummett. I will call the criterion of application. So a category P is defined by laying down its criterion of application and its criterion of identity. Now, I will, if I have a minute left here, finish by reaching the point of going into these things. Namely, one may wonder, in this form of judgment, which is the same as S colon P, of course, just notational difference. Does this form have two or three meaning components? On the surface, of course, it looks as if we have S, it's one component, P is one component, and we have the copula here. And similarly down here, it seems as if we have 1, 2, 3 things here, and then we have the definitional equality form, which has 3 places. That would make 4 components in that case. Now, I want to give an argument why the copula is not meaning carrying, so that there are only 2 components here and 3 components here. And that means that the conceptual situation comes out better if I use a kind of geometrical notation, 2-dimensional notation, rather than the linear notation. I think that the way to analyze this form is to think of it as it's a form, namely the form of being a P, and this form, illustrated by the big circle here, has a hole in it, and that hole is filled by the subject. This fits with what I said about the definition of a category a moment ago, because a category P is defined by explaining what it means to be a P, and what it means to be two definitionally equal P's. And hence, it's being a P which has meaning. So it's all of this which gets a meaning. But just ask what does it mean to be, not, well, the immediate answer, what do you mean? I mean, you cannot ask me what it means to be. You must be to be something, some P at least. And hence, this is the reason why there are only two meaning components and why the copula by itself is not meaning carrying. So maybe since we are over, yeah, then I could at least finish this point. 2 more minutes here. So corresponding to this, for the second formal judgment, we have the same situation then, that we have a definitional equality form, which is this form, definitional equality between two P's, and the argument places then are these two holes that may be filled by S1 and S2 to complete the judgment. Now the reason why I'm explaining this is because in the following 2 lectures I will make a specific model construction for intuitionistic type theory, so we have to understand what a model is in general. And a model, as we know from geometry, comes about by giving the basic concepts of the theory in question another meaning than the usual meaning. I will follow the practice then of using a star for the interpretation. So now I hope to have convinced you that this is not meaning carrying. We could just as well take it away. And if we now are going to reinterpret this, to give it some other meaning here, well, then this will have to be compositional in the sense that we will get the interpretation of S in that other model, and the P here will become instead some P star in the model, and similarly down here we will have S1 will get another interpretation and S2 will get another interpretation. And the P will get another interpretation, P here. But you see there is something that we cannot, whose meaning we cannot change. Because we start with a judgment here, which may be of either of these two forms, and we try to give it a new meaning here. But what stands on this side is again a judgment. So the notion of judgment is not reinterpreted. And similarly down here. This is again a definitional equality judgment now with a change. The category has changed its interpretation to P star, but it's still a category. So the following notions remain the same in any model. Judgment to begin with. Then category. So not only P, but also P star here is a category. And object, because S is here reinterpreted as S star, but it remains what stands in the subject position of this judgment. So it remains object. And then we have identity between objects, if I call it identity now rather than definitional equality, identity between objects. These four notions, they are so basic that they resist any kind of reinterpretation. And for those who remember the title of the book that Wilfred showed in the beginning, it has the title Epistemology and Ontology, versus ontology. These are precisely the epistemological notions of logic, or of this particular logical system. And it's these epistemological notions that resist any kind of reinterpretation, whereas the ontological notions, the notions of set, element, relation, etc., function, etc., they are always possibly reinterpreted in a non-standard model. Thank you.
Just a quick clarification. Do you intend the equality sign to occur in the lower right without a star, or with a star, or not at all?
So originally we had both. So the sign for the judgmental equality is equal. So these belong together.
Okay.
And we have three places then that we can let them fill here. But then there was my argument that we should rather think of this not as having three places. We should rather think of whether or not I write out the colon here as one form with two holes in it.
Yeah.
And your question was?
On the right hand, on the right hand side, you have neither the colon nor the equality sign.
Yeah.
But the P star can't be the same as the one above, because now it's in two places.
No, exactly.
So there must be something different happening below.
Yeah, exactly. So as I said, a category is laid down by explaining what an object of the category is, first thing, and secondly, what it means for two objects of the category to be the same. So there are two forms corresponding to P, and these forms are what I've indicated. So here we have a hole, and then we have the other one with two holes in it. And I've allowed myself to use the same symbol P there.
In your statement of Theorem 1, did you intend a quantifier on R to be inside the scope of the left, inside the left scope of the implication?
Now, the scope of the quantification over R is all of this.
But don't you want to say that for every R, this relates, R relates the x's to the x primes and so forth, implies the conclusion?
It's stronger than that for each R.
Yeah, for every R, yes. For every R, if these are related.
If a single R does it, then the conclusion holds?
No, this is universal.
Yes, but that's in the... If you push that quantifier in, it's
Yes.
equivalent to saying there exists an R such that R of the x's and x primes implies the conclusion on the right.
And he's
That's right.
No,
saying that for every bijection is stable by every phi is stable when you apply bijection.
Does sigma possibly depend on many different R's?
so let's see now. Sigma. Now, sigma does not depend on R, as I remember it. So R appears here because it's here. And this just says that for all isomorphisms R, if these are related, then sigma of them gives the same truth value. And you say that if we have a universal quantifier here, we could move it in as an existential quantifier before the implication. And that is certainly true, but it doesn't change the interpretation here.
There was another thing. Will you guys collect the questions and we'll take you at the end, okay?
We have just one. Tell us when it's out there.
Okay. Any questions here?
I have a question, if you don't mind. I just can't resist. So you had a box at the beginning, and you had a horizontal line between logical and non-logical concepts. And I feel like somehow in the 90s everybody was trying to erase that line, and now in the noughties, the zeros, everybody's trying to draw that line again. And the reason for that, as far as I can tell, in stuff I know, which is the code community, is because above the line, in the logical field, you want things to have proof irrelevance. So proof irrelevance is something you really do want when you have computational interpretation of your logic. And below the line, you want related questions like large elimination. And so all of a sudden, I mean, it's not really backpedaling, but people realize that there are some important differences between what's above the line and what's below the line. And so, do you think that's relevant to this discussion of logical and non-logical constants?
I understand perfectly well what you are referring to, namely that in some situations we are not interested in the computational content of the proof. So it's enough for us if we have some indication of just that there is some proof. We don't want to see it.
Sometimes it's harmful because if you accidentally compute proof, then you're losing time.
Yeah, right. Now you are posing a question which is new to me, namely whether that is relevant to this discussion originating with Tarski. I just can say spontaneously that I haven't even thought about that, which seems to indicate that spontaneously I would say, no, I don't think that is connected. But it's safer that I try to think about it until Wednesday.
So should we give ourselves a short break of 5 minutes?
Better to continue directly into 6, I think.
Okay. No break. Okay, so earlier on in the talk you had this grid, and there was some question of where equality should go. There was one option was putting it in the interpreted logical box, and then the other was putting it in the uninterpreted non-logical box. And here, where we've got the two different pieces of a category, it seems like we're not allowed to reinterpret equality, and that seems like we're choosing the interpreted logical box. And I was wondering if you could say something about why you want to make that choice, if I've understood that correctly.
Well, so that I can answer immediately and easily, namely that we have both judgmental equality, which is the same as what I have called definitional equality most of the time here, and propositional equality, namely the binary propositional function that we call equality in predicate logic. And what I said in connection with the fourfold table had to do with the second, that is the propositional equality, whereas what I said here had to do with judgmental equality. So these should not be mixed up.
We get the question from the Institute for Advanced Study. Okay, your turn, Andre.
Yeah.
This is Andre Bauer at the Institute for Advanced Study.
Actually, it's not quite me. It's Hello. Hello. I have just a simple question about your graphical notation. If you had something more in mind with that, if you think it can be carried out further formally.
Now, the graphical notation here was merely used to try to explain in a pedagogical way what is the meaning structure of the judgment in question. And it was not at all meant to be a formal notation. It was precisely its informality that was supposed to help in making the point that I wanted to make. So as soon as one has given that informal explanation, I would immediately go over to actually writing, instead of this, write that in a normal linear notation. It functions in precisely the same way as this two-dimensional notation functions. And similarly, in the equality case, I would write, instead of this whole, I would just write S1 within parentheses, and instead of this whole, or this whole here, S2 in parentheses, and then the form is here, and the P labels that form that carries precisely the same information as the notation that I used here. So it was not at all meant as some kind of formal notation. It would be very, very cumbersome to work with a two-dimensional geometric notation.
Okay, we don't have any more questions over here.
Thank you.
Well, I'll keep going a little bit with the question I asked before. So what we're saying then is that these interpretations need to preserve judgmental equality. What would go wrong if we allowed propositional equality to be interpreted as, I'm sorry, judgmental equality to be interpreted as propositional equality?
What will the first thing that will go wrong is that instead of a judgment, an equality judgment, we will get a proposition instead. So we are somehow blurring or trying to ignore the fundamental difference between proposition and judgment. And of course that is at the very heart or starting point of type theory. I mean, the notion of a judgment was more or less dead in logic before I decided to revive it in connection with type theory, because I needed some term for these things. And I could have chosen assertion rather than judgment. Frege used Urteil, judgment, but Russell made it into assertion because the term judgment was such a loaded term at the turn of the century in Britain, because it was so strongly connected with the British idealists of the 19th century that Russell and Moore wanted to clean their hands. And Russell found this very good term, I think, assertion, which I could have used just as well if I had wanted. But I thought that there was so much good terminology that had been developed from the beginning with Descartes, roughly, up to and including Frege and Husserl, so let's say up until the Second World War in the German-speaking world. Like forms of judgment, for instance. Well, anyone who has read Kant's Kritik der reinen Vernunft takes that as a completely standard term. Of course, it could be forms of assertion, but then you don't get these associations to Kant, which is exactly what you should get if you think of my explanation here, how the notion of category is connected with form of judgment. The first place where we have seen that connection is in Kant. Kant arrived at his categories by looking at the forms of judgment of the logic of his time and then replacing the logical terminology by a more ontological terminology, let's say, and that became the names of his categories. So I wanted to keep alive this idea that categories are related to forms of judgment, and then it's not so good to call them forms of assertion. Yep.
And we thank Per very much.